Okay, just have a look at this first. Just try and think, can you fill in all the boxes? What should go where? So a distance time graph, flat line means the object is not moving. Gradient of a distance time graph gives you the speed. And the area under the graph gives you nothing. Okay, it doesn't actually mean anything. Whereas for a velocity time graph, a flat line means you've got a constant velocity. The gradient is going to give you the acceleration. So if it's a negative gradient, that means it's a deceleration. And the area under the graph is going to give you the distance travelled. And generally, when we're dealing with terminal velocity style questions, we tend to be dealing with this stuff, the velocity time graph. Okay, so we've got to think about what the shape is going to tell us about the motion. Okay, so here we have a velocity time graph of an object which is falling. Could be a skydiver, could be a rock, could be whatever, it doesn't really matter. All we know is the object is falling and we want to see what's happening to its velocity. Before we do that, often a question will ask you to describe the shape of the graph. Okay, if the question asks you to describe the shape of the graph, make sure you describe the shape of the graph. Okay, lots of people will talk about the speed changing over time, stuff like that. If you're asked about the shape, talk about the shape. Okay, so here the shape is, there's initially, probably one L, steep gradient. Okay, so this early area here is you've got an initially steep gradient. Okay, it's almost linear. And what happens? Well, over time, the gradient will decrease. I can't see the purple on the blue. Never mind. I lined it yellow. There you go. There you can see it. So it decreases over time, and then eventually gradient goes to 0 because it becomes a flat line. Okay. Rounding out of space. Okay. So we're asked to describe the shape, talk about the shape. Okay. Initially, you've got a nice linear high gradient, and the gradient reduces, gets lower and lower and lower and lower and lower and lower and lower, so the gradient becomes 0. Then it might do some other stuff, but that's just the shape we're looking at. So if it talks about the shape, okay, and focus on that. Same graph, if you're asked to talk about the motion, what's happening, again, you break it up into bits. Okay, so initially, what happens? Well, let's say it is someone stepping out of an aircraft. Okay, that's what aircraft look like. Done a degree in aeronautical engineering, so I'm allowed to draw them like this. I'm not sure that's a window, maybe a wing might be helpful. So there's our aircraft, and the person steps out. Initially, as soon as you step out, you're not moving downwards. Okay, it's a bit like Wile E. Coyote when he runs off the cliff, looks down and starts to fall. Initially, you've got 0 vertical speed, unless you're climbing, but we'll leave them on that. So you've got 0 speed, okay? So initially, your weight is much greater than your drag, okay? So whenever you're doing a terminal velocity question, you're generally talking about forces, okay? So you're going to accelerate downwards. How do we know we're accelerating? Well, we know we're accelerating because the speed is increasing, okay? Speed is increasing all the time, okay? At no point in this graph does the speed decrease, so you're accelerating all the time, okay? As the speed increases, so does the drag. Yeah, and you've all experienced this. If you're driving through town, you put your hand out the window, you can feel the drag of the air. If you're driving on the motorway, you can feel the drag more because you're going faster. Okay, so speed increases, so does the drag. This means the resultant force is decreasing. Okay, so if the resultant force is decreasing, then the acceleration is decreasing. how can you tell that the acceleration is decreasing? Well, the gradient is getting flatter and flatter, so you can see that from the graph. Okay. And then eventually we're going to get to a point where the drag force is going to equal the weight force. Okay, so at this point we've got no resultant force. And if you've got no resultant force, you've got no acceleration. Okay, if you have no acceleration, your speed isn't changing. Okay, so you've reached your max velocity, which often we call terminal velocity. Okay. So yeah, you're not going to go faster. Your drag equals the weight, no resultant force, no acceleration. You reach the maximum velocity or the terminal velocity. And we can see that on the graph because the line goes flat. If we wanted to figure out what the terminal velocity was, we just read it off on the graph. It'd help if we had a scale. Never mind. So that's how you talk about it. So I've made about 8 points there. Often that's worth 4 marks. And this is where the word salad comes in. People just start writing down lots and lots of stuff. But essentially, if we go back through it, okay, key points, weight is greater than drag, you accelerate, you see that on the graph, speed increases, drag increases, resultant force decreases, the acceleration decreases. Remember, at no point are you slowing down, you're always gaining speed, but you gain speed less rapidly as your acceleration decreases. Eventually, drag equals weight. This is the point that most people get about terminal velocity. Okay, the drag equals the weight. No resultant force, no acceleration, max velocity, terminal velocity is reached, line goes flat. Now, sometimes we're not dealing with stuff falling. Sometimes we might be dealing with something as simple as, brace yourself for an awesome diagram, car driving along a road. Okay, car will have an engine, and the engine will provide a certain amount of force. Okay, so initially, okay, there's not much drag acting because it's moving quite slowly. Okay, again, as speed increases, the drag will increase. So let's say we had a certain amount of driving force from the car. Okay? So from the engine, applied through the wheels to the road. Okay, as you get faster, you get a bit of drag, then you get a bit more drag, and then you get to this point where at some point drag equals a driving force. So very similar to our falling object. Okay, we've got 0 resultant force. So we've got no acceleration. Okay, so we've reached our maximum speed. So it's pretty much the same thing, isn't it? You've got a certain fixed force. Here it's our driving force. Before it was our weight. You've got drag, which increases as you go faster and faster. As the drag increases, the resultant force is decreasing. Eventually the resultant force becomes 0. When the resultant force is 0, we get no acceleration, we've reached our maximum speed. The problem people have when they go from the falling one, which we tend to hammer a bit, to something like the car that's driving along, is they start talking about weight and stuff like that. You've got to make sure if it's a car, it's not its weight that's moving it faster unless it's falling out the back of an aircraft, okay, or off a cliff. Generally, it's the car's engine applying some driving force to the wheels, which is, moving it along the road. Okay, so that's terminal velocity. Just remember, a word salad is not tasty or nutritious. Okay, it just means you're not going to get the marks. Okay, but think about what you write. Okay, write in bullet points. Okay. Tell you what, let's make that a bullet point. Write in bullet points. If it's a 4-mark question, then heck, make 4 bullet points. Okay? But just keep it simple, stick to the physics, and you'll be fine.